All right, these are your lecture notes for Learning Target 3. It's going to follow the notes of Glencoe 13.2. Please notice there are several definitions for you to record before we start looking at Example 1. In Example 1, we are asked to draw an angle in standard position, and what that means is I just need to show the rotation of an angle here. Whenever I'm drawing the rotation, it's important that I'm always starting on the positive x-axis where y would be 0. All right, so if I'm doing 240 degrees and we start to rotate, let's just go right here. So far, I have rotated 90 degrees. Well, 90 degrees is not yet 240 degrees. Now I've rotated another 90 degrees, and I'm not going to go a full 90 degrees because so far I've rotated 180. And the difference between 180 and 240 is a distance of 60 degrees. So this is my full rotation. He's essentially 60 degrees away from the x-axis, and that's just one thing for you to notice. If we're looking at negative 30 degrees, okay, notice that a negative rotation is actually not going to rotate me counterclockwise. That'll actually rotate me clockwise, okay? So positive was a counterclockwise rotation. If I'm rotating 30 degrees, I actually don't need to rotate all that much. And so this is approximately a rotation of negative 30 degrees, where we are 30 degrees away from our x-axis, okay? For 450 degrees, notice that this is greater than 360, which would be a full rotation, aka a full circle. So no matter what, I'm going to do a full rotation in a counterclockwise motion. So far, I have gone 360 degrees. Now I'm trying to figure out how much further do I need to go to hit 450. Well, I only need to go about 90 degrees more, so I go to 90 degrees, and this is my full rotation. I can just do a little right angle mark here, showing that I am 90 degrees away from the x-axis. All right, so now in example 2, we're going to look at converting between degrees and radians. So in A, I'm given 60 degrees, and I'm asked to convert that to radians. Well, the formula to convert something into radians will be by multiplying it by pi over 180 degrees. An easy way to remember this is because your units, one needs to be on top and one needs to be on the bottom in order for it to cancel out. All right, so now when we multiply fractions, we multiply straight across. So that's going to give me 60 pi over 180. And now this I can be simplified because 60 divided by 180 is going to simplify to 1/3, which is why the radian equivalent for 60 degrees is pi over 3. Please note that your textbook actually discussed what radian was, and remember that radians are just the measure around the circumference of the circle. All right, if we're looking at the next one where I'm going from radians to degrees, now we're going to multiply this by 180 degrees over pi. The reason I'm doing this is because the pi's will cancel out. So then I'm just going to multiply straight across. And so on the top, we're going to have negative 7 times 180, which gets us negative 1,260 degrees. Notice that because I use radian or degrees up here, I now have a degree symbol for my answer. Well, this is going to reduce to negative 315 degrees. All right, so now we're going to take a look at our real-world problem in example 3. Find both the degree and radian measures of the angle through which the hour hand on a clock rotates from 1 to 3 p.m. All right, so a clock is just a circle. And if we're thinking about each quadrant of our clock, think about the fact that there are 12 hands. So essentially you're looking at 12 portions of the clock, okay? So the distance from 1 to 3 o'clock would be 2 lengths of a rotation between hands, or 2/12 of the portion of our circle, which is just going to simplify to 1/6 of our circle here, okay? So a full rotation around the circle or the clock would be a rotation of 360 degrees. I need to figure out what portion, 1/6 of this portion would be the distance from 1 to 3 o'clock. So I'm going to cut this into 6. 360 divided by 6 gets me 60 degrees. So the rotation would be 60 degrees. But notice that to go from 1 to 3 o'clock, we're going in a clockwise rotation, so it's actually going to be a negative 60-degree rotation because I'm going clockwise. Now, it did also ask for the radian equivalent, and if you recall from the previous problem, we actually already converted 60 degrees. It converted to pi over 3, but this one will convert to negative pi over 3, and that'll be the distance that it rotates. All right, the very last example for 13.2 deals with finding coterminal angles. And what coterminal angles really are is just another angle or another measurement that's going to share the same values as the other guys, aka they will be the same distance away from the x-axis, and as you're going to learn tomorrow, they're also going to share the same sine and cosine values. So we're first looking at 240 degrees. Recall from the very first example that our rotation here looked a little like this, and 240 degrees was 60 degrees away from the x-axis here. Now, to find coterminal angles, I need to do a rotation, okay? The first rotation I'm going to do is I'm going to take 240 and I'm going to do another rotation, aka add 360 degrees to get back to that spot that I was once at, okay? So 240 plus 360 degrees, aka one full rotation around the circle, is going to get me an angle measurement of 600 degrees, okay? Now, if I want to go the other direction, if I'm at 240 and I rotate backwards, aka I'm going in a negative direction, I'm not going to add 360. I'm going to take away because I'm rotating in the opposite direction. So 240 degrees minus 360 degrees gets me negative 120 degrees. So both of these angles are called coterminal angles for 240 degrees because they share the same standard position around the axes, and they're also the same distance away from the x-axis. All right, for the last part of this problem, we're going to use the same strategy, but now we're in radians, okay? So 360, the reason we were using that was because that was one full rotation around the circle. Well, when we're in radians, instead of adding 360, I'm going to add 2 pi. And instead of subtracting 360, I'm going to subtract 2 pi from whatever the radian is that I'm currently located at. So we're dealing here with 9 pi over 4. So I need to find a coterminal angle that will share the same position via rotating around the circle either in a positive or a negative direction, okay? So it'd be helpful to get a common denominator here. So 2 pi, that can be really represented as 8 pi over 4, okay? So let's first deal with our top problem. 9 pi over 4 plus 8 pi over 4 gets me 17 pi over 4. The next one, 9 pi over 4 minus 8 pi over 4, well, notice that got me pi over 4. And the question did ask for me to end up with one positive and one negative measure. Because that did not give me a negative measure, I need to subtract 2 pi again, aka subtract 8 pi over 4 again from pi over 4. Okay, so now we have pi over 4 minus 8 pi over 4, getting me negative 7 pi over 4. Okay, so our angles that are coterminal with 9 pi over 4 are 17 pi over 4 and negative 7 pi over 4. But please notice that pi over 4 is also coterminal with this angle. I'm sorry, let me clarify. It's coterminal with this radian measure.